Thank you, Alia, even if you're not with us. Thank you again for this live walking around Ljubljana. Okay, now we continue with professionals lectures. The first one, namely Typology of Building Structure and Strengthening Techniques in Slovenia, will be given by Marjana Lutman. Marjana Lutman is the head of the section for building structures and earthquake engineering at the TAG. She has been employed at TAG for more than 35 years. Her main focus is in the field of behavior of masonry and reinforced concrete building under Seismic. She participated in the reconstruction of the Posočje region after the last destructive earthquake in Slovenia. She had led and participated in several national and international research projects related to civil engineering. As an introduction to Marjana's lectures, we prepared a video of the city of Ljubliana as a fairly vulnerable and heavily populated area. The most typical structural types are highlighted according to the typology of building structure throughout history. Some of them have already been seen in the previous Alia's video. Thanks at this point, Andras Krivic, for making this video. Okay, let's see the field exam. Now I'm inviting Marjana Lutman to join us. Marjana.
Yes, hello. I'm glad. Thank you for the word. Thank you for your kind introduction. So I will share this screen, and we shall go through the typology. Just wait. I think that we see the. Is it okay?
We can see the presentation.
Yes, perfect. You have already introduced myself. Thank you, Maya, very kindly. As already said, I have been working in this field of building structure all the time, in particular in seismic issues. So the typology of the building structure is the first part of my presentation in Slovenia, in short. And here we see the map. Past earthquakes, namely, had a strong impact on construction practice in seismic codes, also in Slovenia. With regard to the number and intensity of earthquakes, the territory of Slovenia is quite an active area. On this map, there are epicenters here and intensities of past earthquakes. The strongest one here with the red point, it was in 1511 Idrija earthquake in the western part of Slovenia. It has affected a large territory between Carinthia, Friuli, Slovenia, and Croatia. Here on the right side, we have a timetable besides the map, and there are years of earthquakes on the left side and the years of issuing seismic codes on the right side. After the last destructive earthquake in Ljubliana, already mentioned in 1895, the building ordinance was respected. After the First World War, its rules were abandoned or forgotten, and a long period without seismic codes followed. Although after the Second World War, a large number of buildings were constructed. Only in some rare cases, a very low horizontal seismic load has been taken into account. However, after some significant earthquakes, a temporary code came into force in Slovenia in 1963, and then a year later, a federal Yugoslav code. Due to some uncertainties and some anomalies with its application, the code was revised in 1981. The revision was strongly influenced also by earthquakes in Friuli in 1976, which destructed also some parts of northwestern part of Slovenia, the Posočje region. Then Eurocode was used for some structures in Slovenia even before its beginning of mandatory use in 2008. For example, it had to be used also for the seismic rehabilitation of Posočje that was hit by strong earthquakes again in 1998 and 2004. So let's go a little bit back to our old buildings. Here is an example of the oldest buildings. It is the castle of Idrija, already mentioned, with connection with the strongest earthquake. It was built after that earthquake, not built by an aristocratic family, but for the administration of mercury mine, actually also for the safe storage of mercury. Today, the castle hosts the Idrija Museum as a town of UNESCO World Heritage, of presenting its technical history. It is actually a Renaissance castle with 3 defensive towers and a small clock tower. A Baroque renovation followed in the 18th century. In particular, courtyard was renovated with semi-circular arcades and Baroque paintings. The last thorough renovation took place between 1988 and 2070 for today's museum. Regarding the structure, it has strict foundations, walls, and even columns that are supporting arcades are constructed of stone masonry. Original walls above basement and first floor were preserved, while wooden floor structure, as in other buildings above upper floors, were replaced by reinforced concrete slabs. Here below, we have a picture of Križanke complex in Ljubljana. It's even older. The original part of monastery was severely damaged in Idrija earthquake in 1511. It was then reconstructed many times, lastly by the Slovenian famous architect Jože Plečnik in 1952. The load-bearing walls in this complex and other buildings of this age are typically constructed out of two outer layers of irregularly sized uncoarse rubble stone. Between these two layers, there is an infill consisting of smaller stones in a poor lime mortar. Cut stones were used only at the corners and the wall intersections. Regularly cut or partly cut stones in a compact mortar was used only in case of public or monumental buildings. That period after Ljubliana earthquake between 1896 and 1910 is known as the revival of Ljubliana. It is significant urban and architectural development, important steps in seismology and building construction, and a social progress too. In those 15 years, more than 400 new buildings of size like this were built, and hundreds of buildings were renovated or extended, all in the Vienna secession style. Typically, they have basement, ground floor, and 1 to 2 floors above. Ground floor or first floor in some cases have a larger story height, but not always. It is typically between 4.5 meters up to 5 meters. Then after the Second World War, a floor was added in some buildings, like here above on the right side in the case of Principal Courthouse building. All those buildings were constructed following the building ordinance from 1896. It is a very prescriptive type of code for solid bricks masonry buildings which prevailed at that time. By this, 3 main structural characteristics have been achieved for an adequate seismic behavior. The first feature is the regularity in elevation. The thickness of structural walls gradually increases from the basement, where it is at least 19 centimeters, to the top floor, where it is up to 45 centimeters. So we see this on the elevation plan on the left side. Following this rule, the masses are smaller in upper floors where seismic acceleration are higher, and consequently seismic forces will be smaller and distributed more regularly. And not the least, the structural walls are uniformly loaded not only by seismic load but already of the gravity load. The next structural feature is the regularity in plan. There are thicker, called main structural walls we see in each wing in longitudinal direction. These walls support floor structures, jack arches, or timber. Beside these main walls, there are so-called connecting walls, which are usually thinner. They're sometimes only 15 centimeters thick. But They are very important because they limit out-of-plane deformation of main walls and actually contribute to the seismic resistance in their direction. They can therefore not be treated only as partition walls, but they have a structural meanings, although they cannot be treated as structural to the current codes. So the next feature is structural integrity. Integrity which has been achieved by means of wall ties and anchors. We see below two pictures of these steel elements. They were placed actually in the middle of the thickness wall at every floor levels in order to prevent separation of walls and enable their potential seismic resistance of the wall can be fully utilized. Now we go further to the period between the world wars. Here are two buildings. In the front, we see the building of the Bank of Slovenia, which was built in 20s of the previous century. It is quite irregular in plan, in elevation, not here in front, but behind, where there are some parts which are not equally high. Regarding the structure, reinforced concrete has been used in Slovenia for floor structures and cupolas already before the First War, already in the first 2 decades of 20th century, also in this building. But the vertical structure, walls and even columns are masonry, constructed out of solid bricks. The difference is from previous period that the strength grade of bricks and mortar increases from the lower floors to the upper floors. So when the need is higher, the strength is higher. Here behind this building, we see the famous skyscraper of Ljubliana. It is not known only as the tallest building in the Balkans at the time of its construction, but it is well known since base insulation has been applied in the practice for the first time in the world. Besides, the whole structure is made of reinforced concrete columns and beams with the infill walls. So in the 30s, actually, this type of structure began. And here is an example. One of the first buildings with reinforced concrete columns. For this building, it is typical that reinforced concrete beams connect reinforced concrete columns only in a longitudinal direction. We see along the wing. But in the transverse direction, there are only ribs of the reinforced concrete rib slabs, which are here as floor structures. Yes, here the next one, also grammar school. It is famous because it's an international school of Ljublana grammar school. It was designed by architect Emil Navinšek. His schools are very, very well known as corridor-free architectural system, without corridors, but in structural sense, it differs from the previous one. Namely, columns here are not connected only in one direction, but in both directions in plan. Although the floor structure are also as made as ribbed slabs here. Now we go after the World War II reinforced concrete frame structure, as here in Parliament left above, and the school building next to it. They were publicly and they were their structure are made of reinforced concrete. In the middle. Actually, in the 60s, a lot of school buildings like this one in the middle above were built all over the Slovenia, and it is also typical because of being without corridors. The problem of these first reinforced concrete column buildings are that they are very slender, especially in the longitudinal direction. So it is the weakest direction in case of earthquake. On the other hand, residential buildings were still mainly constructed out of solid brick masonry. Even some high rises here on the right side were constructed around 1960. They have 10 floors above the ground floor. The vertical structure consists only of solid brick masonry without any tie columns. Only 2 steel rods in each corner were placed. But 3 strength grades and of blocks and 3 classes of mortar were used in this building. That was the progress, and the masonry of higher strength is in the lower floors, of course, and the masonry of lower strength in upper floors. So it was a very optimized way of using available cement, which was a very rare material in those times. These high rises were designed to withstand a little horizontal action, not without it, according to a German standard, but only to 4% of the weight of the building. So we come here to our first national seismic code. Both of them, which were enforced in Slovenia before the adoption of Eurocode, required the analysis and some minimal requirements. Among others, the first one limited the number of floors of masonry buildings. For zone 9, in which Ljubliana was situated here on the map on the left side, only 3 floors above the ground level were allowed for plain masonry and 5 floors for confined masonry. However, according to our experience, some requirements of this code have not been always respected. Many improvements were brought about the revised code in 1981, and although brick masonry walls were mainly replaced by reinforced concrete shear walls in that time in residential buildings, revised code reduced the maximum number of floors for masonry structures again. In zone 9, plain masonry structures were no longer allowed. For the zone 8, where Ljubliana was seated on the new map on the right side, only 2 floors above the ground level were allowed for plain masonry and 4 floors for the confined masonry. There were also some new minimum requirements for reinforced concrete structures, which actually prevented some anomalies observed in the previous practice. So here are typical buildings in the period that followed. In the 60s, residential buildings were still built of masonry up to 5 stories as allowed, but it was confined with reinforced concrete bond beams here on the left above. Besides, brick and mortar of higher compressive strength were used in the lower floors. In the early 70s, like here above in the middle, the reinforced concrete replaced masonry. Shear wall structure prevailed in residential, school buildings, like here below in the middle, and other public buildings, while frame structure were mainly used for industrial and commercial buildings. Here is an example of the influence of revised seismic code entering in 1981 with regards to the minimum amount of reinforced concrete shear walls. Namely, these are two adjacent multi-apartment buildings in the same neighborhood with the same architecture as we see on the pictures, and reinforced concrete shear was constructed with the Otinor technology, which was very famous at that time. In both buildings, there are plenty of these Otinor walls here in the picture in vertical direction, namely about 4% of the floor area. The problem here was the amount of transverse walls. In the building on the left, designed before 1981, the area of this walls amounts only to 0.25% of the floor area. All other walls in this direction are partitions or made of masonry. The newer buildings on the right was designed after 1981, and there are reinforced concrete walls instead of partition walls and the masonry walls, and their area amounts to 1.5% of the floor plan as required by the revised code. That is significant difference in seismic resistance. So then reinforced concrete shear walls was the prevailing type of structures designed after 1981. They were verified also for shear forces, not only to bending moments as often previously. Many of such residential buildings do have shops and other service premises in the ground floor and garages in the basement. This is a problem because there are reinforced concrete columns in the lower floors and reinforced concrete shear walls in the residential floors, and it usually brings irregularity in the structure, in elevation, and consequent problems with higher deformations already for vertical load. So the second part of my presentation with regards to strengthening techniques are shown here. Actually, these techniques in Slovenia were developed already in the 70s of the previous century after many earthquakes which mainly affected rural areas and smaller towns, not Ljubliana. Some drawbacks which were observed of stone and brick masonry buildings, which were typical buildings for those areas, were observed after earthquakes. First, it was observed that inadequate structural resistance of masonry walls is present, and it reflected in typical diagonal shear cracking and disintegration, like here we see. And the second inadequacy is that it is the lack of connections between structure walls and the lack of connection between walls and floor structures. And this feature allows, as always, out of plane vibration and the separation of corners and walls, and finally collapse of the walls. First strengthening techniques were therefore developed for masonry structures and were widely practiced in Posočje region, already mentioned, northwestern part of Slovenia, hit in 1976 after Friuli earthquakes, which caused significant damage. The most common technique for providing adequate structure integrity is placing steel bars on both sides of the wall, interconnected with stirrups. They are fixed at corners and intersections of walls, you see here on the right. For that purpose, they are threaded at both ends. Then they are fixed onto the steel plates and slightly prestressed by means of nuts. It will be more details given by my colleague Mateusz Bergant later. Regarding the foundation, actually they were rarely the reason of inadequate seismic behavior of the buildings, but however, after the upper structure is strengthened and it is stable to resist higher seismic forces, there is again the need of strengthening the foundation. And the most common technique is the new reinforced concrete tie beam along existing foundation wall. Systematic grouting of stone masonry with cement mixture is intended to fill the voids and connect all components of the masonry into a whole. By this measure, the tensile strength of the wall can be increased by up to 2 times in case of very poor masonry. Sometimes even more. The details of these techniques will be, as already said by Matthias, explained and presented by Mr. Bergan. And I would only like to address that after the latest earthquake in that region, the procedure of the assessment of the effectiveness have been induced. Here on the pictures on the right side, we see that for that purpose, the control hole are made into the previously grouted masonry. And from the appearance of the surface of that hole and from the appearance of the core taken out of the masonry, we can assess and judge about the effectiveness, how the grout has connected all parts into the unity. After 1998 earthquake, in Posočje region, designer have already measured to make design verifications. And after the Second World War, second earthquake, already by Eurocode 8. And all houses in that region were verified, which were intended to be strengthened. For that purpose, they needed mechanical characteristic about the masonry in original condition and in grouting. Therefore, in situ testing have been carried out in typical houses in the town of Bovec, like here, this building and around it. Here is one of the buildings where in situ testing took place. It was previously a police station. We will see it later again. One specimen was tested in original state, but it should be without cracks. And the other specimen was grouted. Both specimens failed in shear, like the pattern it was observed, and the tensile strength of masonry in both states were evaluated. And by means of comparison of the results, we see that tensile strength is increased by around 80% in case of residential houses and even more than 100% in case of public buildings. The next measure is reinforced cement coating. It is used for stone masonry walls if it is previously grouted and if there is a need for further increase of load-bearing capacity, or for solid brick masonry which cannot be grouted. By the rule, the coating is placed on both sides of the wall, and both coatings are connected together by means of anchors. In this traditional version, the coating consists of steel mesh in a cement mortar. Besides, the carbon fiber reinforced polymer or glass fiber reinforced polymer coatings are also possible and are beginning to be used in Slovenia. In one of Ljubliana's buildings from the 30s, we performed in situ testing and evaluated the effectiveness of this measure. 2 specimens were tested, first in original condition and then strengthened with carbon fiber strips, which fully wrapped the wall. And as seen from the diagram here, this measure improved the lateral capacity of the wall by up to 60%, but it is important that it reduced the formation capacity by more than 3 times. Therefore, it is important that such a measure is placed on all walls in the building in order to prevent spoiling the original regularity of the structure. And here is the slide showing an extensive experimental research that has been recently carried out in the laboratory of ZAR, addressing the effectiveness of carbon fiber reinforced polymer if applied to hollow brick masonry. The damage of this full-scale model was typical for masonry structure in original and in strengthened state. Much larger drifts and damage developed in the first floor, the diagram on the right below, than in the upper two floors. One of the final findings was that the lateral resistance of the structure has been increased by around 50%. But we must keep in mind that this result is only valid for this type of strengthening applied to this type of masonry. So I would thank you for now. I hope I'm in time, and I give the word back to my colleagues. Thank you.